Hey everyone, in this section we're going to be working with more differential equations. This time we'll have a little more context for them. There, how about the title for today? Specifically, the context we're going to be working with are either exponential growth or exponential decay. So the first thing I want to draw your attention to is this differential equation right here. dy dt equals k times y. This would be any situation where something's rate of change is proportional to the current amount present. So again, if we were to translate this into words, it would be the slope is equal to, k would be like some constant of proportionality times the amount y, whatever's actually there. So the first thing I wanted to do was just solve the general form of this differential equation really quick. So here it is. We want to solve, get y equals something. So like we've been doing, let's separate the variables. We can multiply both sides by dt. And then let's divide both sides by y. And now I think we're ready to integrate both sides of this equation. So we have a linear thing on the left in the denominator. So remember, that's going to be the natural log rule. Don't forget the absolute value. And then k is just a constant. The dt would turn into a t, a linear one. And then don't forget there'd be some constant of integration. And that's why k is used instead of c, because then otherwise if you integrate, now you got two c's, that's just confusing. From there, if we wanted to solve for y, well, we'd have to get out of exponential, or I'm sorry, we'd have to get out of logarithm form, wouldn't we? We'd have to get to exponential form. So our base here is e. Then, let's see, log base answer equals exponent. So all of this stuff is my exponent. And then the inside of the log was my answer. So for simplicity's sake, how about we flip this around? And then I'm also going to expand the plus c part. So way back in like algebra 2, you probably talked about how like x to the m times x to the n is the same thing as x to the m plus n. I'm going to use that rule in reverse. So here's what we're starting with. I'm going to go backwards. So I'm going to say times e to the c. Well, e to a constant is still a constant, yes? So I think we can further reduce this to be e to the k t times some new constant, which is typically their initial condition. Which I'm going to use y sub 0 or y naught to stand for. So if we were to update this just a little bit more, we'd say absolute value y equals, I'm going to move this to the front as well, the initial amount of y times exponential with whatever that exponential growth or decay constant is times time. And then finally, if you want to get rid of the absolute value, you know, you should switch to the other side to be plus or minus. Typically, most contexts use the positive values. So really the general solution here is just y equals y naught e to the k t. However, you can always check. You can check if it's positive or negative by subbing in the initial condition. By subbing in. Hopefully that makes sense. So here's our general solution to this form. And again, this will hold whenever we have something where its own rate of change is proportional to how much is there. This is typically used for population models. It can be used for, there's some electricity stuff we'll bring up in our third example. Anything without with it, where the upper limit isn't too important, because obviously exponential functions grow forever. So here that is again for you on the next page. Here's your general solution. Or sorry, here's the differential equation. Here's your general solution. C is the initial condition. And then as you remember from pre-calc, depending on whether that exponent is positive or negative, that represents growth or decay. And so here's the nice thing. When you're working examples, let's read through example 3 real quick. Suppose population grows according to the equation here. How long will it take for the population to double? This question did not specifically ask you about using the calculus to get there. So, if you can correctly identify, hey, this is an exponential differential equation, if the problem doesn't specifically tell you to solve it using separation of variables, you can jump straight to the fact that you know what the differential equation solution is. Now, of course, if it did say something like use separation of variables, then of course we would have to integrate by hand, but it doesn't. Okay, well, let's pull out the useful information here. That 0.1 is meaningful. There's our k. And then it says, how long will it take for the population to double? It doesn't give you an actual amount. Good news, that's okay. So how about our final amount for the population should be double the initial amount. Hopefully that's fair. If y not, y sub 0 is our initial amount, then can't our final value here be 2 of them? So 2 of them equals 1 of them times e, 0.1 times t. And so then this is a problem I could have given you last year. At this point, we can divide both sides by whatever the y naught is. In this case, and that's why it doesn't matter that we don't know what it is, because we'll just divide it out right away. And then you've got an exponential equation, which, let's see, the base on this is e. So I'd say natural logarithm of the answer 2 equals the exponent. And then let's divide off this extra thing here. Multiply both sides by 10, or divide both sides by 0.1. Now, you push it into the calculator, you'll get your exact answer would just be that. If you want the 3-decimal approximation, that's 6.9. Oh, I scrawled it really small in my notebook here. I think 6.931. And let's see, it doesn't... I really should have put units for time in here. Because normally you'd say like days, hours, minutes, seconds, whatever. I guess since there was no context, you wouldn't have to answer with context, but you've come far enough through calculus with me that you know when there's context, you need to answer in context. Let's see, our second one is a similar problem, just worded slightly differently. Whoops. So let's take a look here. A puppy weighs 2 pounds at birth, and then 3.5 pounds 2 months later. If the weight of the puppy during its first 6 months is increasing at a rate proportional to its weight, then how much will it weigh when it's exactly 3 months old? So let's see, what's the key phrase here? Increasing at a rate proportional to its weight. Increasing at a rate proportional to the amount. That sounds like an exponential rate, or sorry, an exponential differential equation, doesn't it? So we know the solution to that differential equation is the amount at some later point in time equals the initial amount times e, and then our exponential constant times time. And again, this is probably a problem I could have given you last year, aside from the fact that we might have to identify this key first step. But afterwards, we've really got 2 points. We've got at time 0, we've got a weight of 2, and then at time 2 months later, we have a weight of 3.5. So I think we can use these 2 points to figure out the k, and then we can finally figure out what it is at 3 months. So let's see. This one's nice. Since this is our initial condition here, we can just jump straight to saying y naught is 2, and then we're going to use the second one to help us find k. So if I was to substitute in here, I'm going to use the second point for y and t. So we'll have 3.5 equals initial amount times e. Don't know what k is, but that's what we want to find. 2 months in. So let's divide both sides by 2. Now again, the variable I want is in the exponent, so let's take a logarithm here. Log base e of my answer equals my exponent. So let's divide by this 2 as well now. Or can I just write it as this? And I'm just going to caution you here. If you punch that into your calculator, you will get a decimal approximation. That's fine. What I'm going to caution you on is, remember, this is a number that's going into an exponent. And so you really do not want to round this number early. If you're going to write down the decimal approximation, go crazy with the digits. I'm serious. I'm talking like probably 5 or 6 at a minimum. Because here's why. Let's finish off solving the problem. So we wanted to figure out the amount after 3 months. Well, that'd be amount equals initial condition times e to the whatever you plug in for k here, which honestly, this is exactly how I'd type it into my calculator. What was it, 3 months? Yeah. And if you punch it in directly like this, you know you're going to get 100% the right number because you didn't even round what's in your exponent. But if you misround k, or if you round k too early, and then you end up multiplying it by 3, and it's just a little bit too big or too small in your exponent, that can very, very easily throw off any of your decimal point digits over here. So I would very, very, very strongly encourage you to not turn k into a decimal approximation. I would leave it in exact form. And I really, really want to show you the difference here, but, well, my calculator's been setting up the main window for about 5 minutes now, and, well, this computer works so much faster when I'm on the school network than when I'm on my home network. So I wanted to show you that. I'm sorry. You can play around with it. You punch it in, round it to different decimal places, see how it affects your answer. And yeah, again, my advice would be use the exact version, don't use the approximation. Okay, one more. So suppose electricity draining from a capacitor. Okay, so this is some physics here. That's okay, we can still do the math. At a rate proportional to voltage V across its terminals, such that this. Okay. Notice this is in the same form as what we wrote earlier, dy dt equals k times y. So I know the solution to this should be exponential. Oh darn. Solve the differential equation for v. Shucks. Okay, so we have to do the calculus this time. No big deal. We know how to do it. Let's start with that differential equation, dv dt. Let's separate our variables here. So I'm going to divide both sides by v. I'll multiply both sides by dt. And now let's go ahead and integrate both sides. Zoop, let's see, negative 1/40th times t. And then don't forget the constant of integration. But we want to solve this for the voltage itself. So let's get out of exponential form. 1/40th t plus c, which if we use the same trick on the plus c, the initial condition here, can we say the absolute value of the voltage is that constant, or perhaps, no, sorry, it's not that constant exactly, so I probably shouldn't reuse the letter. How about, let's say, the initial amount times that stuff. And again, if this bugs you, just go back 2 pages to the argument we made here. We said e to the c, well, that's still a constant. Oh, by the way, that constant is the initial condition. I'm doing the same thing here. E to this c is some initial condition, so that's what I'm replacing with here. And again, this is just kind of a physicsy thing, but it doesn't really make sense to have a negative voltage. You can, but let's not use that in calculus. So let's just say voltage is the initial amount times the exponential stuff. Okay, then we have a follow-up question. How long will it take for the voltage to drop to 10% of its original value? So to 10% of its original value, that makes me think that the final voltage would be 0.1 of the original amount. So let's sub that in up here. 10% or 0.1 of the original equals original times e to the exponential stuff. And once again, this is at this point, it's a problem I could have given you last year in pre-calc. Divide out that number, take a logarithm, log base e of the answer equals the exponent. Multiply both sides by negative 40. And we've got our value for time, which punch that one into your calculator as well. You might think, uh-oh, I got a negative out here, I'm going to have a negative time. Nope, it's okay. Remember, the natural logarithm function is negative when the input is less than 1. So we're good. 2 negatives are going to cancel out, make a positive. This one comes out to a little bit more than 92 seconds. Okay, that's it for today. See y'all tomorrow.